Kinetics. So although we can know a lot of things about a chemical reaction, so the reactants, the products, stoichiometry, energy, we really need to understand the rate of the reaction to really understand what's happening in the reaction. So although graphite can be compressed into a diamond, the reaction is so slow we can't even view it in our real time. So we're not going to be focusing on those kind of reactions in this course. We're going to be looking at the kind of reactions that occur in real time. The difference between thermodynamics and kinetics is that thermodynamics can tell us if a reaction occurs, whereas kinetics tells us that a reaction occurs at a certain speed or how quickly it goes. So this first reaction here is a very depressing reaction for my wedding ring. A diamond reacts with oxygen to produce CO2, so it literally blows away with the wind. This delta G, which we're going to learn about more thermodynamics, tells us that it's spontaneous. The fact that it's negative, and it's very large negative delta G, will actually say it's very spontaneous. Spontaneous meaning it can occur. It's a really good thing we have kinetics, which says it occurs very, very slowly. Whereas this reaction, my delta G tells me that, yeah, it's spontaneous, it's kind of spontaneous, but it actually occurs instantaneously. So there's going to be a big difference between if it occurs and how quickly it occurs. So what we're going to focus on right now is how quickly. So reaction rates. These are a change in concentration of a reactant or product per unit time. So when we're talking about these concentrations, we're going to use these brackets. So yes, moles per liters is molarity, and we can use the terms molarity. But in writing, most of the time, we're going to use brackets around whatever compound we're talking about at that time. If the rate expression involves a reactant, we have rate equals a change in the amount over a change in time. This is always going to be negative because the concentration of our reactants must decrease. If a reaction is occurring, we have to be using up reactants. That's what a chemical reaction is reactants becoming something new. So therefore, the concentration of that reactant is now gone. So when we do this, we're getting an average rate over an entire reaction. To get an instantaneous rate, if we look at a graph, we can look at tangent lines. So what is the rate at this point versus this point? Okay, we have a change in rate over time for many types of reactions. Now in your lab yesterday, we looked at different types of graphs for different kinds of reactions. The fact that this is concentration versus time means this could be used as a test for a zero order reaction. If this had been a straight line, meaning a tangent line would have been the same throughout, the rate would have been the same throughout, and that would have been called a zero order. We're going to be using this terminology a lot. But because this is not a straight line, we do have to use tangent lines at any point. If I want to know what the rate is at 400 seconds, it's a very different rate than all the way at 2,000 seconds. So because of all these complications, we're going to be looking specifically at initial rates. The rate of a reaction is not going to be constant, it changes with time. But if we work with initial rates, we don't have to worry about the reverse reaction. So when I introduced you to equilibrium, we talked about the fact that many reactions do go forwards and backwards. But when we're going to be doing kinetics, we're going to be focusing on the forward reaction rate. So examining the rates of reactions. So I have this reaction here. My reactance is obviously the downward slope. This is what is going away in concentration. This is what is increasing in concentration. Now what you notice is that we have different colors occurring here, or different changes in slope. Without even looking at the reaction, you could figure out the mole ratio here. So let's look at why. Well, as my NO2 decreases, my NO increases at the exact same rate, or the exact same ratio. For every one of these that goes away, we gain one of these. So we have a 1-to-1 ratio. However, it takes two of these going away before we even gain one of these. Notice how the slope here, I have a half of a slope of an increase of O2. So the ratio here is 2 to 1. If I look at the chemical equation, that makes sense. For every 2 NO2s, I produce 2 NOs. Hence why their slopes are the exact same. But for every 2 NO2s, I only produce 1 NO, or 1 O2, which is why it has half of an increase of a rate as the decrease of the reactants. So rate laws. Okay, we're going to look at different ways to bring our rates into calculations with these equations. So rate laws can express how quickly a reactant is consumed or the rate at which a product is produced. Specifically here, we're going to be looking at the consumption of reactants. Okay? Now, knowing the rate at which a product is produced is important as well. And we're going to be able to look at that later on. But for now, we really want to look at how much or how fast are we consuming up those reactants. We're going to have two different ways to look at rate laws. We have differential rate laws and integrated rate laws. Differential rate laws are a rate law that expresses how the rate depends on concentration. So rate depends on concentration. When we're looking at differential rate law, this is what we're going to be specifically focusing on, is concentration. Integrated rate law is going to focus more on the time influence. So when I write out a differential rate law, we always write it the same. Rate equals little k. This is crucial that it's a little k. If you actually put a capital K, you'll be entirely wrong. Because unfortunately, kinetics uses a little k for its constant, and equilibrium uses a capital K for its constant. And k's look pretty similar. Make sure you don't make yours look similar. This must be a little k. So rate equals little k times the concentration of your first reactant to a power times the concentration of your second reactant to a power. Notice dot, dot, dot. Okay, if you have 5 reactants, you put each reactant to the power. And we're going to talk about that power in just a second. But remember, these brackets are going to represent the molarity, or the moles per liter. So if I have the rate law, rate equals K, A to the m power, B to the n power. These exponents are going to be positive or negative. They're integers or fractions, but most of the time they're going to be positive and usually whole numbers. 0, 1, 2, 3, meaning 0 order, first order, second order, third order. So those exponents are going to be my orders. When K is going to be my rate constant. The value of K depends on the type of reaction, the temperature, and the presence of a catalyst. Okay, a type of reaction is going to be very important. A combustion reaction, you all have experienced many combustion reactions on the 4th of July. Those are pretty instantaneous. They're pretty fast. Okay, temperature is going to be very crucial. We're going to discuss this even more. But just to give you an idea, usually about a 10-degree increase is going to double your K. Okay, so temperature is highly, highly important when we're talking about the rate of a reaction, which also means you must keep constant temperatures in these reactions. And then the presence of a catalyst, because these energy diagrams aren't going away. Remember, a catalyst will lower this, which means that the reaction is able to occur much quicker, has a much lower hill to go over, so it's going to occur a lot quicker. So all 3 of these can easily change your K. And then this part right here makes for a very easy multiple choice question. Which of these reactions occurs the fastest based off their K only? Well, whichever one has a larger K occurs fastest. So the order of the reaction comes from the exponents. The sum of the exponents is the order of the reaction. So we have order of each reactant, and then we have an overall order of the reaction. So if I look at this rate law, this would say it's first order in terms of A, because it only has a 1 exponent on the A. Second order in terms of B, and third order overall. 1 plus 2 is 3. Okay, just add up the ones, add up the exponents, it gives you your overall order. Now the units of K can be calculated, and the units of K generally are their own point in every free response question. But if you calculate them on your own, they're pretty complicated, and they take a lot of time on their own. Notice, if I was trying to calculate the units of K, if I was given the concentration of A, the concentration of B, and the rate, this would be moles per liter per second, divided by moles per liter, divided by moles squared over liters squared. And this would be entirely different for each reaction based off of the units for each one of the, based off the order for each one of the reactants. So instead of practicing that and trying to work those out, there is a simple way to figure out the units. The shortcut is just to know this. Okay, your unit for K is always going to be liters to the X over moles to the X per time. And what this X is, it's 1 less than the order of the reaction overall. So if you can just learn this, then you can just automatically discover the units for your K every time. So if the reaction is third order, then 3 minus 1 is 2. You plug a 2 where those X's are. If it's second order, 2 minus 1 is 1. Put a 1 where those X's are. If it's first order, well, 1 minus 1 is 0. Putting a 0 would be L to the 0, moles to the 0, which is the same thing as 1. So it'd be 1 over time. The last one I left for you on your page is, what is 0 order? Well, let's look. 0 order, K, equals L, 0 minus 1 is a number. L to the minus 1 over moles to the minus 1 times time. If you put this, this would be entirely correct. You, however, will not see it like this very often, because having something to the negative 1 exponent would be the same thing as having it equal to moles over liter per time. Which makes sense. When we looked at 0 order reactions on our graph, we found that it was the concentration per time, moles per liter per time. So for differential rate laws, we said it was changing the concentration. And what was the effect on rate? What was the effect of concentration on rate? So in order to determine this, we're going to do experiments in which we hold some concentrations constant and change others, and look at the effect on rate. If doubling the concentration of a reactant doubles the rate, then it's first order, because there is a direct relationship. Okay, so right here, we have a direct relationship. If doubling the concentration causes the rate to quadruple, then it's second order. So you multiplied it by 2, and that made the rate multiply by 4. That is an exponential relationship. That is an exponential relationship of 2. Well, it's second order, which we write as an exponent. If doubling the rate, or doubling the concentration, increases the rate by 8 times, well, 2 to the third power is 8. So this would be exponential change of 3, and we would call it third order. And if doubling the concentration doesn't change the rate at all, okay, you double the concentration and the rate stays constant, that'd be the same thing as putting something to the exponent of 0. The rate stays constant. Okay, anything to the power of 0 is 1, so it's a 0 order. Let's go apply this to some data, and it comes really quickly. So if we look at this data here, the first concept is, of course, the fact that we must keep one of these concentrations constant in order to test the effect of the other one. So if I want to test what changing the concentration of A does, I must keep B constant. So I want you to write on your page exactly how I write to make sure you follow along. So if I want to test A, I must keep B constant. I must find an experiment in which I keep B constant. Here and here, I didn't change B at all. So therefore, any change that occurs in rate was caused by a change in A. So from here to here, I doubled the concentration of A. That's the only thing that changed, so this must be the cause of a change in rate. My rate changed by 4, a multiple of 4. And now where you find your order is from the exponent. Remember, order is an exponent. So 2 to the what power would create a 4 change? 2 to the second power. So A is second order in terms of A. The reaction is second order in terms of A. Now if I want to see what the reaction is in terms of B, I need to change B, but keep A constant. So in this case, I keep A constant for the first 2 trials, and I changed B. I changed B by a multiple of 2, and the effect that had on the rate was also a multiple of 2. To find the order, you look at the exponent. 2 to the 1 power would equal a 2 change in the rate. So it is first order in terms of B. Now write the rate law. Well, the rate law would equal rate equals little k, always little k, so rate equals little k. Put your brackets around your first reactant, A, your brackets around your second reactant, B, and put everything to its order. So we said A is second order, B is first order, so it'd be A squared times B. And finally, this reaction is third order overall, because I have a 2 here and a 1 here. So 2 plus 1 gives me third order overall. So for the next one, your first step is to look for where something's being held constant. So if I want to look for NH4, I want to see what the order of NH4 is, I need to look for a time when NO2 is held constant. NO2 is held constant from trial 2 to trial 3. And here I multiplied by 2 my concentration of NH4. I look at the rate. My rate also multiplied by 2. So 2 to the what exponent equals 2? 2 to the first exponent. So 2 to the first power or first order. Therefore, NH4 is first order. Do the same thing for NO2. We find a place in which NH4 is held constant, like trials 1 and 2. From trials 1 to 2, I multiplied the concentration by 2. If I look at the effect on rate, my rate also multiplied by 2. So 2 to the what order would equal 2? 2 to the first order. So the reaction is first order in terms of NO2. Write out the rate law. Rate equals little k, concentration of your first reactant times concentration of your second reactant to the power of their order. Rate equals little k, concentration of A times concentration of B. And the reaction is second order overall. Now, these questions are generally multiple choice type questions because they're just conceptual application. Can you read it and answer the correct answer? So from here, this becomes a problem when we have these exponents, because in the multiple choice section of the AP test, you do not have a calculator. So you need to be able to manipulate these exponents into a way it's easier for you to figure out what happened. So from trial 1 to trial 2, I had a change in 2, and I need to be able to look at this and see what the change was. The fact that this is a -4 exponent, this is a -3, usually makes it difficult for people. You have two options here. Either one, turn these into decimal form and it's easier for you to see, or move these decimals where it's basic math for you. So if this is a -4, and I want to make this a -4 as well, I can move my exponent over here to make that a -4. 3 going into 12, well, that's simple math. 3 to 12 would be to 4. So 2 to the what power makes a 4, 2 squared. That makes this reaction's rate law be rate equals the concentration of A squared. So here's the AP problem from 2003, directly from the AP test. Now when you first look at this, you are given the data table. What's different than the ones we've looked at so far, it has 3 different reactants, so each time you want to look for a change in rate, you need to hold 2 of the others constant. So the first thing it asks for is to find the rate of the bromine, or the order of the bromine, the bromite, and the hydrogen ions. So for bromine, we need to find a time in which the other 2 are held constant, which was easy from experiment 1 to 2. We held the bromite and the hydrogen ions constant. So we just look at the change. That was a change by 2. This was also a change by 2, which means it is first order in terms of bromine, or bromide, the ion. Now your reasoning here would be it is first order because doubling the concentration of the bromide ions doubles the rate if the other reactants are held constant. Notice how it said to show your reasoning. So it is first order because doubling the concentration of the bromide doubles the rate if the other reactants are held constant. So if we want to do bromite, we need to find a time when both the bromide and the hydrogen ions are held constant. Now these experiments are independent of one another. A lot of times people are looking for only 2 that are right beside each other, but you could have done these experiments in any order, so you can pick any of these 2 experiments. So if I want to look for bromite, I look for a time when both the bromide and the hydrogen ions are kept constant. So in trials 1 and 3, both of them are held constant. I look at the change here. Now this is a free response question, so you would have a calculator for this one. This is a change times 1.5. Going from trials 1 to trials 3, the rate increased by 1.5, which if you look at the exponent here, the exponent would be 1. Therefore, the bromite is also first order. Your justification would be it is first order because 1.5 times the concentration of bromite makes a 1.5 times the rate if the other reactants are held constant. If the other reactants aren't held constant, then we're going to have a lot of changes in rate. That wouldn't work. So it's if the other reactants are held constant. Now for the hydrogen ion. The problem with the hydrogen ion is there's not a time when hydrogen is doubled and nothing else changes. Which means we're going to have to find something new to look at. And what we're going to do is, because we know that these two are first order, we're going to have to take this change into account first before we look for any new change. If we didn't know that what the other order of the other compounds were, you couldn't do this. So if I'm looking for a time in which hydrogen changes and maybe only one of the other ones change. So let's look here. Okay, from here to here, hydrogen doubles and bromide is kept constant. So if we look at bromite, it also changes, unfortunately. So let's take this into account first, because we already know bromide is first order. And because it's first order, we can take into account the effect caused by bromite first. So bromite was multiplied by 2 here, which means the rate should have been multiplied by 2 just from the bromite. Before anything else happened to it, the bromite would have multiplied the rate by 2, which would be 3.75 times 10 to the negative 4 times 2, which is 7.5 times 10 to the negative 4. If changing the hydrogen had no effect, then this would have been the rate, and the change in rate would have only been caused by this. But notice how the rate is still higher. It's 3 times 10 to the negative 3rd power. So what happens is the rest of this change, going from 7.5 times 10 to the negative 4th to 3 times 10 to the negative 3, the rest of this change is caused from this. So in this case, we doubled this, and you can use a calculator at this point in the test, and you would find that going from 7.5 times 10 to the negative 4th to 3 to the negative 3rd is a change of 4. So the rest of this change was caused just by the hydrogen, and that was exponentially 2 times the change. Which means that the hydrogen has a second order. It's a second order because doubling the hydrogen quadruples the rate of the other reactants if the other reactants are held constant. So this is the perfect right order, the perfect right answer for this question. However, if you don't have time or you can't see a way to answer this question, you would have had 2 options if you were taking the AP test. One of those options is not to skip it. Skipping in the free response section is a terrible idea because you can no longer complete the rest of that problem. Your 2 options are: 1, try and figure it out logically, put some kind of answer from the logic you know, or 2, throw down an answer. There's only so many orders possible. You probably won't get the correct answer. If I would have guessed first order because most reactions are first order reactants. So I would have put first order and I would have moved on with my life and gotten the rest of these points. And I would have missed 1 point on the entire problem, because as long as I used the rest of this problem saying that hydrogen is first order, I would have gotten everything correct. Now, if you solved it and you found that second order, you get all the points. But don't ever skip a problem. Always put something. Try and use logic to guess it. If you put 20th order, that would be pretty illogical. I've never even heard of that. You should never see that. So try and put a logical answer and move on if you don't have time or you really can't seem to find an answer. So the next step, write the rate law. Rate equals little k times concentration of the first reactant times concentration of the second reactant times concentration of the third reactant, each to the power of their order. So rate equals little k, concentration of bromine times the concentration of bromite times the concentration of the hydrogen ion. The hydrogen ion was second order, so you put it to the power of 2. If you had said it was first order, you would put a 1 there. And you would have still gotten it right because you understand how to apply the orders into your rate law. If you changed it, if you said it was first order on part C and then said it was second order here, then you would now miss this question as well. You need to show that you consistently understand the concepts. The reason why they give you the points if you put a 1 here is because you understand the concept that if it's first order, you put a 1 above it. And then lastly, determine the value of the specific rate constant for the reaction at 298K. Include correct units. This is 2 points here. 1 for solving for K, 2 for the units. So what you do here is you pick any experiment and you plug and chug. Any of these. And then you put this here, this here, this here. Oh, and let's put the rate over there. That's all you do, plug and chug. So solving for K is very easy. That's why you need to know the little hint for finding the units, because that's your second point here. So my units are going to be, well, I'm fourth order overall. So that would be liters cubed, right? 4 minus 1 is 3 over moles cubed times time. You got to figure out what time they're using. So look at what they used. Oh, there we go, seconds. This is actually the harder point on this problem, is to get the units. So if you pick any of these experiments, so I picked the first one, I plug those into the rate law that I already put. Once again, if I'd put a 1 here and I still calculated everything using a 1 for the exponent, I would still get all the points because I'm correctly applying the lab data into the given rate law. I plug everything in. I do all the math. I get 5,000. And then using my little trick for the units, I get my units as liters cubed over moles cubed times seconds. Otherwise, if you didn't use this little trick, you would have plugged in moles per liters per seconds here, moles per liters, moles squared over liters squared, divided all this under that, and tried to figure it out. It takes a long time, and there's a lot of really simple mistakes you can make trying to cancel out all those units. So I highly suggest spending the little bit of effort to try and get this whole thing in your head. Liters over moles per time, then whatever these two powers are is just 1 less than the overall order. So the integrated rate law. The difference between the differential rate law and the integrated rate law was yesterday when we talked about differential rate law, we said it's different concentrations. Differential rate law is different concentrations. We do the same lab over and over again with different concentrations and compare the rates from that. An integrated rate law is that the change in concentration is integrated into your lab. What we do is we look at a change in concentration over time. So we express how the concentration of the reactant depends on time. Now it's going to depend on what reaction we're doing for which rate law we're going to use. If the entire reaction occurs in 2 seconds, trying to do an integrated rate law is not going to work. We can't look at a change in concentration over 2 seconds without some really high-powered technological equipment. So if the entire reaction occurs in 2 seconds, we're just going to keep using different concentrations and use that data to see a change in rate versus concentration. Otherwise, we can do a change in concentration versus time if we actually have a way to measure changes in concentration over time. So the ways we can do this would be pH. A change in pH would tell us how many hydrogen ions are there. That would tell us change in concentration. Another way to do a change in concentration is using a spectrophotometer. The wavelengths are going to bounce and give us certain different measurements based off of concentration. So next week in lab, you're actually going to do that. You're going to use a spectrophotometer to measure changes in concentration over time. So the rate law we're going to choose is going to be determined by the experiment. If we can conveniently measure how the rate changes as the concentration changes, we can readily determine using a differential rate law. On the other hand, if it's more convenient to measure the concentration as a function of time, we can determine using an integrated rate law. So there's going to be a lot of different factors for which we use. If the reactant is really expensive, we don't want to do the differential rate law. Keep making different concentrations over and over and over again and do the lab. We'd rather do the lab once, take our measurements once, and save our money. So the first order integrated rate law. Now this is the form that used to be taught. The form of the equation has actually changed on your AP test now. We're going to write this in here. It's the same one that I gave you on the lab, and it's also on the bottom of page 4. It's Ln, concentration of our substance at a certain time, minus Ln of our concentration of a certain compound at the beginning. So to the O is our initial, equals negative KT. This is the exact same equation, just manipulated differently. This is the way it is given to you on the AP test. Some people find it easier to calculate using this way. Some people find it easier to calculate using this way. Whichever way you find it easier, feel free. Now, because this one isn't given to you on the AP test, the way I learned it was not TKT. NaOAT, not E equals KT. Not DKT. Okay. Now, or this one doesn't have a way to memorize it, but you don't need to. It comes on the AP test. Whichever way, you'll find the same answers. So let's make sure we understand what each one of these mean on here. So, actually I'll put it just down here. Concentration at T is concentration at a specific time. Concentration O is my initial concentration. K, you should already know, is a rate constant. Little k, it has to be little. T is obviously time. Now Ln, those of you who haven't gone all the way through with Algebra 2 yet, you probably haven't worked with natural log yet. All that we really need to know for this course is that there's a pretty little button on your calculator that says Ln. Okay? If I want to get rid of the Ln, I do the opposite of an Ln, which is a little e to the power of. On your calculator, that's right above the Ln button. Okay, so as long as you can get used to doing that, using it just like a regular logarithm, that's a natural log, but you're going to act like it's just like a log. You're going to do everything the same way you would do if it said log, just use the Ln button instead. So a plot of Ln A versus T always gives a straight line for a first order reaction. For the M&M lab, we decided it was a first order reaction. We got a straight plot. Now, while that wasn't an actual chemical reaction, it works. First order means it depends on concentration. It directly depends on concentration. The more M&Ms we have, the more M&Ms will show an M when you roll them out. Okay, the less, the fewer. It's a direct correlation between amount of M&Ms and the amount of M's you see. Same thing with the direct correlation between the concentration and the rate. So that's why our Ln versus T gives us a straight line if it is first order. Like I've said before, about 80 to 90% of all reactions are first order. That's why we focus on first order first. At 400 degrees Celsius, the first order conversion of cyclopropane into propylene has a rate constant of. Now this is a lot of words with a lot of numbers, and these kind of questions can get kind of overwhelming pretty quickly. You have to identify what each of these words and numbers are as you read through to kind of give you an idea of what the heck you're supposed to be doing. So first of all, it says it's first order. Let's keep that in mind. It has a rate constant. Well, we know that rate constant is little k. So we've been given a k. Here's the number for it. If the initial concentration, okay, well we know what initial concentration is. That's that A to the O. Initial concentration of cyclopropene is, gives us a number. Awesome. What is the concentration, what will the concentration be 24 hours after the reaction begins? So it's asking for a concentration at a specific time, which means our unknown this time, so our x is going to equal the concentration at a specific time. That's our AT. And we were given the T, 24 hours. We have a T, we have a little k, we have our AO, our starting AO. That means we're going to use our naughty-Katie or the first order integrated rate law as given on the AP test. You're going to plug each one of these in. Now, I want you to be careful with units real quick. If you notice, this is in hours, but my K is in seconds. So we need to convert our hours to seconds. So 24 hours converts to 86,400 seconds. Now I want you to try this using either one of the equations. Okay, it's very important that you practice this and see if you can get the correct answer, because a lot of people struggle with this natural log at first. They completely understand the concept, but they can't get the calculator to do what they know. So let's go through and practice this problem. Plug in what we know into either this equation or into the AP equation. So I'm going to show you both ways. Let's start with plugging it into naughty Katie and see how that one works. So I plug in each one of my units. So I have Ln of the whole thing. My initial concentration I got here, I plugged it in, equals my K, got from up there, and my T, I had to change it into seconds. The reason I had to change it into seconds is because now these two units cancel. So all I will have left is the unit of molarity, which my answer is supposed to be the 4 molarity. So that's right. Now, where I see a lot of people struggling here is what the heck to do with this Ln. So what we have right now is Ln times all of this. You know from your math class, I can't do anything to anything that's inside of these parentheses until I get rid of this Ln. To get rid of this Ln, I put everything on this side, e to the power of. In your calculator, just second of your Ln gives you e to the power of. So that's all you have to do to get rid of the Ln. That gives you a number. Then you have 1 times 10 to the negative second over AT equals your number. So that's just basic algebra. And you get 0.905 times 10 to the negative third. Notice my unit is already taken into account here because of the brackets. The brackets mean concentration. So this is saying the concentration of A is 0.905. Now if you use the other equation, I have, so if I use the equation from the AP test, I get this. I plug in, I'll use the term x because that might help. So my AT is what I'm solving for, so I'm going to look at it as x. Minus Ln. My concentration of AO, which was 1 times 10 to the negative second, equals a negative. K was 1.16 times 10 to the negative sixth times my time, 86400. Now if I multiply these two together, I get negative 0.100224. If I put this into my calculator, just hit the Ln button of 1 times 10 to the negative 2, I get negative 4.605, which is subtracting a negative, which is the same thing as adding a positive. So I have my Ln of x minus a negative 4.605. To get rid of the negative minus the negative 4.605, I'll add to the other side, which gives me ln of x equals negative 4.705. Now I'm not done because I still have the ln of x and I just want x by itself. To get rid of the ln of x, I take the other side, e to the power of negative 4.705. Look on your calculator. If you hit second ln, that'll give you e to the negative 4.705. And my final answer comes out to be x equals 9.05 times 10 to the negative third, which equals my concentration of the substance at a certain time, the specific time being 86,400 seconds, if I wanted to designate that on the concentration. So, notice, all of a sudden I switched to chapter 21.2. This is the only thing we're going to be talking about from the chapters 20 and 21. Chapters 20 and 21 is organic and nuclear chemistry, neither of which are on the AP test anymore. So this is the only thing we really talk about with nuclear chemistry is radioactive decay. So every radioactive sample has a decay rate or an amount of particles that will decay over time. This is a first order process. This is a derivative of the Naudi-Katie equation. And by derivative, I mean the only thing that I've changed is instead of using concentration here, I just put the letter N, because we're just looking at numbers. This is actually what I had you do at the M&M lab. We weren't actually looking at concentration of M&Ms, we were just looking at number of M&Ms. So this integrated rate law calculation can be used just looking at the number of atoms of something. So half-life is the length of time required for the concentration of a reactant to decrease to half of its initial value. This calculation right here is one of the easiest calculations you'll ever get, 0.693 over K. And it's given to you on the AP test. You don't even have to memorize this. This is how you calculate half-life. And we also know how to calculate K now. We can use Naudi-Katie, or just the first order integrated rate law. So a lot of times we'll see half-lives depicted as graphs, because it's easy to look at it. You look at its concentration. Half of it deteriorates over a certain amount of time. So the decomposition of SO2Cl and Cl2 is a first order reaction with our K. Well, if we're given K and we're to determine half-life, that's that really simple calculation. Half-life equals 0.693 over K. You were given K, you can do it. Plug it in, voila. 31,500 seconds, or 525 minutes. Or 8.75 hours. Sometimes you might get a half-life question that's it. Just give me half-life, here's K. Oftentimes, half-life is going to be integrated into a problem where you're going to find K first, or you're going to use half-life to find K. If I give you a half-life, then you can find K, then you can use that K to go into an integrated rate law. The decomposition of N2O5 dissolved in CCl4 is first order. Chemical change is. At 45 degrees Celsius, the reaction was begun with, wow, now this is a lot of writing, which means we need to, of course, go through and identify different variables. See what we were given to figure out what they want from us. It gives us initial concentration, okay? So we've got AO. After 3 hours, so we've gotten a time. The concentration had decreased too. Oh, well, we have a concentration at a time. So we have AT. What is the half-life of N2O5 expressed in minutes? It didn't give us K. Our equation for half-life is T1/2 equals 0.693 over K. But it did tell us that it is a first order reaction, and it did give us AO, AT, and T. So we can use our first order integrated rate law, Naudi-Katie, and solve for k. Once you solve for k, then you can plug the k into t of 1/2 equals 0.693 over k. So the radioactive decay of thallium-206 to lead-206 has a half-life of 4.2 minutes. So this is my t 1/2. So I know at some point I'm going to be using the equation t 1/2 equals 0.693 over little k. Okay, and I already have this, so I'll be able to solve for k. Sweet. Starting with this many atoms. Okay, so I have an initial. So an N naught, an initial. So this is my initial of thallium. Calculate the number of atoms left after 42 minutes. So I have a time. I have an initial. And it's asking me to find a number at a specific time. So it's asking me to find NT. Okay, number at a specific time. Well, I can use my half-life equation to find my K, and then I can plug in my K into my first order integrated rate law. So I use my half-life equation. I plug in the 4.2 minutes, and I get my K to equal 0.165. Minutes to the -1. Do not forget that if it's to the -1, this is the same thing as being 1 over minutes. Okay. You're going to see this to the -1 much more often than you're going to see this, because this is a lot easier to write into a computer program. Okay, so any testing program will generally use this instead of this. They mean the exact same thing though. So now that we have our K, we plug that in to our first order integrated rate law, either the ln NO over NT equals KT, or you plug it into the one from the AP exam itself. Okay, they're the exact same, just manipulated differently. I plug in each of these numbers as I've defined where they go. This is crucial that you do this when you're reading a problem. Identify each number in the problem, because even if you read it the first time and immediately knew that this was NO, later on you may accidentally use this for something else. But if you have it written right beside it, just scratched into the question, you're much more likely to not make a simple mistake like that. So you plug everything in, your initial over your NT, your K, and your T at that specific time. How do we know that this is the T at the specific time? Because we put in, and that little t means in at the T, at that time. I solve, and I get 4.89 times 10 to the 19th atoms. A freshly isolated sample of 90Y was found to have an activity of 9.8 times 10 to the 5th disintegrations per minute. Now it sounds like a rate. Okay, so for now, I'm going to identify it as a K. At 1 p.m. on December 3rd, 1995, at 2:15 on December 17th, 1995, its activity was redetermined and found to be 2.6 times 10 to the 4th disintegrations per minute. So I can't have two Ks. So this actually isn't a rate constant because it's changing. This is more like an initial and a rate at a specific time. Okay? An initial and at a specific time. Okay. So instead of it being K, this is my N initial, because N is just a representation of what are we categorizing at this time. Are we doing an amount? Are we doing a concentration? Are we doing number of atoms? Okay. What that means is my first order integrated rate law can now be used to compare any two different specifications at different times. Okay. So my two specifications here are disintegrations per minute initially, so NO, and disintegrations per minute at a specific time. So this 2.6 times 10 to the 4th was my NT at a specific time. The specific time was, let's see, how many days later? 14 days later. And how many hours later? An hour and a quarter later. So a total of 337.25 hours later, this is my new disintegrations per minute. So I have an initial, a final, and a time. Now I can solve for K. Okay. Now it's asking me to calculate half-life, and I know the thing I need for half-life is K. That's the only thing you need to calculate half-life. So you use your Naughty Katie, or you use your AP exam. ln n at a specific time minus ln n initially equals a negative KT. Okay. Plug it into either or. I have my 10.8 times 10 to the 5th was my initial. That would go here. That would go here. My 2.6 times 10 to the 4th was my specific time, so that would go here, or that would go here. The time, once I calculated it, if you put it in minutes, that would work fine. If you put it in seconds, that'd be fine. As long as you had it in 1 unit, you plug it in there, that'll determine the unit on your K. Now I did it in hours, so if you're going to compare your answer to mine, I'd put it in hours. That's my T there. So either way you plug these in and solve, should get 0.011 per hour. I plug my K into my half-life equation, I get 0.693 per hour, 0.011 per hour, and that gives me 63 hours total. If you plugged it in without rounding first, you'd get about 64 hours. Okay. So that means that every 64 hours, half of your Y90 sample has disintegrated. And do not forget about sig figs. When we're dealing with numbers, we've got to be thinking about sig figs here. 2 sig figs here and 2 sig figs here. Those are the numbers that were given to us. So 2 sig figs. Now we have a second order integrated rate law equation and a zero order integrated rate law equation. Our second order integrated rate law equation is 1 over our concentration of AT over 1 over our concentration of AO equals KT. This is the same one that is given to you on the AP test. Now, if you like the Naughty Katie equation, an easy way to remember the Naughty Katie one is because remember that one is not given to you on the AP test, is that the difference between first order and second order is always that second order is 1 over concentration, whereas first order is Ln of concentration. So the only difference between this rate law equation and the Naughty Katie is that instead of 1 over AT, it's Ln of AT minus Ln of AO equals KT. And remember that the plot of 1 over AT versus time gives us our slope, which is K. So if we look at a graph of doing Ln of C4H6 versus time versus 1 over C4H6 versus time, we get a straight line. Now the straight line that is different here than talking about zero order and first order is in first order, my line is increasing. I have a positive slope. So for second order, slope doesn't equal a negative K. Slope just equals K. Another way to remember this is just slope is, or our K is always positive. Now our zero order rate law, this equation looks just like the first order equation given to you on the AP test, except it doesn't have the Ln. Which makes sense because when we think of the graphs of first order and zero order, a zero order graph is always concentration versus time, whereas a first order graph is Ln of concentration versus time. Unfortunately, the AP test does not give you the zero order integrated rate law. But because they give you the first order rate law that looks exactly like this, all you need to remember is change this AT minus AO Okay, change the one that you already have been given that has ln of AT minus ln of AO and just get rid of the ln. Now you have zero order. So each of those equations that are given to you on the AP test, you can manipulate it based off of which order you're working with. If it's zero order, just do AO and AT. If it's first order, use ln of AO and ln of AT. And if it's second order, use 1 over AO and 1 over AT. Those equations work the exact same for each of the equations. Zero order, first order, and second order. All you do is change based off of which order it is. The graph for zero order looks just like the graph for first order. We still have a negative slope, so therefore slope equals a negative k. Page 4 is crucial. These notes that summarize this entire unit must be completely and thoroughly understood. Let's look at each one to begin with. They're categorized by zero order, first order, and second order. Okay. For first thing we're going to look at is differential rate law. Remember that differential rate law means different concentration. That's how we're calculating using differential rate law. We use different concentrations. Whenever you have these, it's just concentration over time, and concentration over time. Our concentration over time graphs will look entirely different based off of the order. If it's zero order, once again, it has a straight line. If it's first order, okay, it swerves. If it's second order, it doesn't. Our integrated rate laws. These are the two that are given to you on the AP test. This one is not given to you. You're going to have to figure it out based off of the two given on the AP test. Okay, remember, take either one of these and change the 1 over A or change the ln of A to just A. Okay. If you want to change between each one of these, just take each of these variables and switch them to the one you need. Our straight line plot. This is very important for zero order and for first order. Slope is a negative k. And for second order, because my slope is positive, just slope is k. I gave you some very simple sample data on how you would figure out based off of different concentrations. Okay, notice when I double this doesn't change at all. It'd be just like being multiplied by 1, which would make the order be 0. Anything to the 0 power would be 1. So it's zero order. Same idea here. If that's doubled, that's doubled. So that would make it first order. If that's doubled, that's quadrupled, which would be why it's second order. Half-life. We only have to calculate half-life for first order equations. This equation is given to you on the AP test. Units of K, this is crucial. Every year people lose lots of points because they can't figure out the units of K. This is one of those things that you can either do it the hard way and try and figure out the units each time, or you can just have this memorized. That one's up to you. Now these little summaries is what I want you to fully understand about each. As in a zero order reaction, the initial concentration of the reactants has no effect on the reaction rate at all. Whether we start out with 10 moles per liter or 1,000,000 moles per liter, the rate will be the same always. For a first order reaction, the initial concentration of reactants is directly related to the reaction rate. So if I start out with 10 moles per liter versus 1,000,000 moles per liter, that rate is going to be exactly directly related to that increase in concentration. This is our M&M lab. Starting out with 100 M&Ms versus 10 M&Ms would have a direct correlation on the rate. And for second order, initial concentration of reactants is exponentially related to the reaction rate. This is why whenever we do our calculations here, doubling this quadruples this, so the exponential difference here would be an exponent of 2. Okay, it'd be second order. Make sure you thoroughly understand all of this. So reaction mechanisms. Reaction mechanisms diagram a series of steps in which a chemical reaction occurs. Reaction mechanisms. It's a diagram of a series of steps in which a chemical reaction occurs. So if my chemical reaction is A plus B plus C makes ABC, the likelihood of that happening in real time is really, really small. Remember when we talked about a reaction, it requires them all to collide at the same time with the correct amount of energy and the correct orientation. So 3 molecules all colliding at the same time is already rare. Now they have to collide at the exact right orientation with the exact right amount of energy. That's not very likely. And what we see from nature, what we see from most chemical studies, is that that's not what actually occurs. Instead, maybe A hits B, which makes AB, and then AB hits C, which makes ABC. So overall, we have A, B, and C, and we end up with ABC. But it really gets broken down into steps. That's what a reaction mechanism is. We're breaking down the overall reaction into what we're going to call elementary steps. Okay, so it's little, small, simple steps, elementary steps. We're going to have what's called an intermediate. An intermediate is a species that is neither a product or a reactant in the overall equation. Okay? What it's something that just comes in the middle. So what I was just saying, if AB collide to make A and B collide to make AB, and then AB hits C to make ABC, well, that AB, that molecule of AB, that only existed in the middle, intermediate. It's not a reactant, it's not a product, it's just a middle step. That's what we're going to call an intermediate. An elementary step is that simple step. It's a reaction whose rate law can be written from its molecularity, aka its balanced equation. So the best reason to make a reaction mechanism, to break down this reaction into its simple steps, is you can actually write the rate law off of just a simple step. And we're going to look at this. The final thing I want to point out is the term molecularity. It is the number of species that collide to produce a reaction. The more molecules that are required to collide for a reaction to occur, the less likely it's going to occur. If you're trying to say that 4 molecules are going to happen to collide perfectly and make a new molecule, that is very rare and very unlikely. So let's look at a visual representation of this. If I have reactants H2 and 2 ICLs, the reality of all 3 of these molecules hitting each other at the exact same time, orientation and energy, very low. Instead, what we see graphically through data is that if we have this first activation energy in which we create one HCl, one of these H2s and an ICL react to form one HCl and one HI. Notice how we have a second ICL that hasn't reacted yet. We had 2. There's still one that hasn't done anything. Now, this ICL and this HI will react to form a second HCl. What we have here is what we call an intermediate. Notice how this HI is not a reactant or a product. It's something that was only produced in the middle. It was a middle step. By one H2 reacting with one ICL, it created an HI. The extra H, the extra I created this unstable molecule HI. This unstable molecule goes and bounces into another ICL, which finishes the reaction, and I get an I2 and 2 HCls. So this is a visual graphically, and let's look at some more visuals. If we have a reaction mechanism in which we have one molecule, that's it. That is the reaction elementary step. We're going to call it unimolecular. Uni always means one. If it is unimolecular, we can write the rate law from its elementary step. Okay. This is why we like elementary steps. If I write the rate law from that elementary step, it's just K of the reactant, K times the concentration of the reactant. If it's bimolecular, I have two molecules reacting, either two A's or an A and a B. Okay. Then if I write the rate law of K, A, B, or K, A squared. Now termolecular, you're not going to see this very often at all. Remember, termolecular would mean three molecules colliding at the exact same time. This is very rare and very unlikely. More likely, one A will hit another A to make AA, and then that AA will hit another A to make AAA. Okay. But if this did occur, we'd write the rate law, Ka cubed. Okay, so you can write a rate law based off only the reactants of the elementary step. So let's look at a visual here. First thing, I'm going to talk about a rate determining step, and this is a perfect visual for that. This tiny funnel is going to be our rate determining step for filling this Erlenmeyer. It doesn't matter if this funnel was the size of a bathtub, the size of the ocean, or just a tiny bit bigger than this one. The size of this funnel has zero effect on the rate, because this tiny little funnel here is my rate determining step. No matter where this funnel is, that will determine my rate. So no matter where your slow step is, that determines your rate, and we're going to write our rate law based off of our slowest step. All right? So I've been talking about this A plus B plus C makes ABC. Okay? Remember, this is just any three molecules combining. That would make one large molecule. Instead of this occurring, because the likelihood of this is very small, we're going to hypothesize that it occurs in two steps. First, A hits B to create AB. Then this free-floating AB will hit a C, and that makes ABC. We're going to call this species right here, this AB, this is an intermediate because it cancels on both sides. It was produced here and immediately used up here. It's not a reactant, it's not a product. It's just an intermediate. And notice, if I take these two reactions, these two elementary steps that add up to my real one, we can see how they add up. By canceling my intermediates, I now have A plus B plus C makes A, B, C. Now the rate determining step, my slow step, has been identified for you, and most of the time it will be. So if you have this is told as your slow step, we can see why. Notice the activation energy required for A to hit B. This takes so much time that the time that this takes is negligible. So our elementary reactions must agree with the balanced equation. All that these reaction mechanisms are is they're a hypothesis. We can test this hypothesis, test what happens whenever we have AB colliding, and then test what happens if we have AB colliding with C. Okay. Another completely viable hypothetical reaction mechanism would be B plus C makes BC, then BC hits A to make ABC. These reaction mechanisms are hypothetical, and you will be asked to write your own hypothetical reaction mechanisms. What you need to be able to do is look at a reaction and break it apart into several steps. And what's important about these steps is that a reaction mechanism must, absolutely must, add up to the overall balanced equation, just like what we did with the A plus B plus C equation. It must add up to the overall equation. There can't be any intermediates. If you add it all up together, all the intermediates must cancel. And then it must agree with the rate law.